So we've already been introduced to combinations. The key thing about a combination is that the order does not matter. So it's when you're choosing items, like we're going to find out playing a game of cards. If you play poker and you get 5 cards, it doesn't matter the order that you get those 5 cards. It's still the same hand. So these are all situations where order does not matter. We've learned about our formula already. All a combination is a permutation with the order divided out. This notation shouldn't have that line there. In some special cases, you have n items. You choose all of them. How many ways can that be done? Only one way, because you take them all. It doesn't matter the order. You just got that group of things. If you have n items and you choose one of them, you have 52 cards, you choose one. How many ways can you do that? 52 different ways. At the bottom here, we have the mathematics that shows why something like 12 choose 3 is equal to 12 choose 9. If you choose, every time you choose a group of 3 from 12 things, you're left with a group of 9 being left. So every unique group of 3 leaves a unique group of 9. So choosing a group of 3 from 12 is the same as choosing a group of 9 from 12. And that can be helpful if you're thinking about more complicated things. Like if I say, what's 8 choose 7? How many groups of 7 can you make from 8 items? Well, you might say, that's hard to think about. But if 8 choose 7 is the same as 8 choose 1, if you have 8 things and you need to choose one of them, that's easy to figure out that it's 8. So 8 choose 7 would be 8 as well. And in our textbook, we saw this example with 10 choose 6 equal to 10 choose 4, with those employees being hired for an arena job. So let's do some card questions. How many poker hands are possible? Well, we have 52 cards. If the order doesn't matter, it will be 52 choose 9. And I think I have this number almost memorized. Can someone check that, how close I am? I know it's close to 2.6 million. So you can play poker almost 2.6 million times and never get the same hand twice. Well, chances are you would get the same hand somewhere in there, but perhaps this is what makes it interesting, is that there's so many possibilities. Is the number right? Yeah? Okay. So we got 2.6 million possibilities. So I could probably right now, if I take out this deck of cards, and I pull out 5 cards. 1, 2, 3, 4, 5. I got the 9 of diamonds, the 10 of spades, the 3 of spades, the 2 of hearts, and the 7 of clubs. You'll probably never see this again in your lifetime. My chances of getting this hand were 1 in 2.6 million, which is really rare. Unfortunately, for those of you that know a little bit about poker, how good is this hand? It's awful. It's like basically the worst hand you could get. But even though it's an awful hand, my chances of randomly pulling this exact hand are 1 out of 2.6 million, just the same amount of chances I would get of getting a royal flush in hearts, but that didn't happen. And so we're going to find out this later this morning about different poker hands. Why is this one a bad? Why is this considered a bad hand? Why are other hands considered better? What's the mathematics behind that? We've also seen questions already like this one where you sort of combine the fundamental counting principle with spaces with combinations. So in this one, we have two decisions to make. We have to choose which boys are going to be on the committee, and we have to choose which girls are going to be on the committee. So we can make our spaces for those two decisions that we need to make. And how many choices do we have for boys? Well, there's 15 boys, and we need to choose 2 of them. And how many choices do we have for girls? There's 18 girls, and we need to choose 3 of them. And every time that you're making more than one decision, you're going to need to multiply in between. They're not separate cases. We don't add up like we do in a cases question. We have to multiply because we've made 2 different decisions, and every group of 2 boys can get mixed with any group of 3 girls, and that makes a new committee. So you type this into your calculator and get an answer. So you've got a class of students. They need to be separated into 3 groups. One group is going to have 8 students, one group 5 students, and one group 7 students. How many ways can this be done? Well, we have 3 decisions we need to make. We need to decide who's going to be in group A. How many choices do I have for that? How many different ways could I put people into group A? I have 20 people in total, and I need 8 for group A. So it would be 20 choose 8. So if this was my class of 20 people and I'm saying, okay, you guys are going to be in group A, anybody could be in group A. So I have all 20 to choose from. And every unique group of 8 people will make all the different possibilities of group A's that I could have. After I've decided who's going to be in group A, I now have to decide who's going to be in group B. Why will this number not be 20 choose 5? 8 people are already in group A. So now, when I look who's left, I only have 12 people left. And I need to choose 5 of them to be in group B. And all the 12 people are left, all the different possibilities of 5 people would be counted there. And then group C, how many ways, without a calculator, can I make group C now? I've made group A. I've made group B. How many ways can I make group C? Right. Just one way. Because whoever's left, right? If group A's been made, group B's been made, and your teacher said, I'm going to put you into 3 groups, and you still haven't picked, and you're like, ooh, I wonder what group I'm going to be in. Buddy, you're going to be in group C. That's the only group that's left. Because there's 7 people. We can write it 7 choose 7. But that's just one, because whoever's left is going to be in group C. So I'd like you to take out your calculator and find this number. And then I want you to ask yourself and do another calculation. Did it matter that I chose group A first? If I chose group B first and did 20 choose 5, would I get a different answer or would I get the same answer? Ask yourself in your mind, should it matter which group I choose first? And then check the math. See if it does matter. Now, another way of thinking about this same question. I decide instead I am going to line up my class from shortest to tallest, and then I am going to cut out 8 letter A's, 5 letter B's, and 7 letter C's. That's not a B. All right. And I mix them in a hat, and I go from shortest to tallest, and I get people to pick out letters as they go. And one possibility is, by chance, everybody picks all 8 A's, then all 5 B's, then all 7 C's. But there's other possibilities, right? I could do that, and I say, let's do this again. In fact, let's try to do this until we've done all the possibilities. Hoy, 99 million different possibilities, and we have to try and get them all, right? At possibility 3,450,000, I say, have we done this one already? Would you be able to remember? No. That would be a terribly long-winded thing to try to do. But if I did it this way, what kind of question is it? It's an identical objects question. It's like a Mississippi question. How do we solve Mississippi questions? Well, normally if we would have 20 different groups, right, which would be a really interesting thing. I line them up from shortest to tallest, and I said, I'm going to put you into 20 different groups. I've labeled A, B, C all the way up to whatever the 20th letter of the alphabet is. What is that? T, U, S, whatever. And I get you to pick. And you'd be like, yay, I'm in group N all by myself. Thanks, Mr. JR. This was really, if you wanted to put us into groups of 1, you didn't need to line us up. But if it was 20 different letters, it would be 20 factorial, right? This is how we do our identical objects questions. But because there's 8 A's, we have 8 factorial that we need to divide by 5 factorial and 7 factorial. And if you type this into your calculator, you get the 99 million again. So what that shows is that sometimes these combinations and permutations questions, depending on your mindset and how you think about them, they can be done in different ways. This question could be done as a combination where the order doesn't matter, or it could be done as a permutation of identical objects. And if you just play around with the formulas, 20 choose 8, remember how to work with our formulas? That you have 20 factorial on the top, you'd have 8 factorial and 12 factorial on the bottom. The bottom 2 numbers always add up to the top number in a combination. And 12 choose 5 would be 12 factorial over 5 factorial, 7 factorial. And 7 choose 7 would be 7 factorial over 7 factorial, 0 factorial. And again, our 0 factorial, which is defined to be 1, shows up in a formula. And if we simplify things here, well, the 7 factorials would simplify. The 12 factorial would simplify. 0 factorial is just 1. And can you see we have the exact same format after it's been simplified as our identical objects. Find the number of poker hands with no clubs. So if I go through my deck of cards and I look for all the clubs, take out the jokers, okay. If we want to count how many poker hands have no clubs, right? I think to myself, well, how could I guarantee that you don't get any clubs? So I'm going to give 5 cards here to Tyson. Did you get a poker hand without any clubs? Wow. Try that again. 5 random cards here. Now I took from the middle and put yours on top, so yours is a new poker hand. Did you get any clubs? No. How did I do this? This is amazing. Pick 5 cards, try to get club. Fail. Oh, did you get a club? No. Wow. How did I do that? Well, I took out the clubs. No matter which 5 cards I give you from this deck, with the clubs taken out, you're not going to get any clubs. But that helps us count it. Because if 39 of them are not clubs and we remove the clubs, and we just say, how many groups of 5 can be made from those 39 cards, all of those will have no clubs in them. And this is a really, really pretty number. Put it into your calculator and enjoy it. Isn't that nice looking? I think that's a very pretty looking number. In fact, that might be my new favorite number for the day. Okay. Now, in the last question that you have in your notes, I'm going to do something different. I'm going to lie to you a little bit. I'm going to, well, I don't know, maybe I won't be lying to you. Maybe I'm lying already. I'm not sure. What's going to happen with this question? Find the number of poker hands with at least 1 club, is I'm going to turn into a salesperson. And sometimes as a salesperson, you have to sell something you don't believe in. I think some salespeople do this. They're like, this is the worst car that has ever existed, but I'm going to tell you it does everything perfect for you because I need to sell this to make some money. So right now, I have 3 different solutions for this question. And I'm going to sell them to you that all 3 are right. But I'm not going to tell you, maybe all 3 are right. Maybe all 3 are completely wrong. Maybe 1's right and 2's wrong, or 2's wrong and 1's right. You have to figure that out. But I'm going to sell them to you that they all make perfect sense, and they are all the best way to solve this question. Are you ready? Okay. We need to find poker hands with at least 1 club. So I'll split this into 3. Here is method 1. Method 1 is an awesome method to use. What you do is you have your 13 clubs. I've already taken them out of my deck. If I want a poker hand with at least 1 club, I need at least 1 club. So what I do is I go 13, choose 1. I take my 13 clubs, I choose 1 of them, and then I take the other 12 clubs that are left and mix them back in the deck. I then randomly pick 4 more cards from my deck. So there's 51 cards in my deck now, not 52 because I've taken 1 out. And I choose 4 more cards. And it might be that I don't get any more clubs. It might be that I get 4 more clubs. But by doing the 13 choose 1 at the beginning, I guarantee myself that I get 1 club. And then in the 51 choose 4, I might get more clubs or not, but I've chosen 5 cards, and this way guarantees that I get at least 1 club. Method 2. All right, method 2, what I'm going to do is I'm going to use some of the math that we already did. Method 2, I'm going to use the not strategy, which is count them all minus the bad ones. Well, if I count all my poker hands, there'd be 52 choose 5. And in part A of this question, we just figured out that there are 39 choose 5 without any clubs. So if I take all the poker hands possible, and I take away or subtract all the ones with no clubs, whatever's left has to have at least one club. Makes sense. And method 3, says, you know what? I think I'm going to break this up and count it as different cases. So in case 1, I'm going to count how many hands have one club. And so if I want just one club, so case 1 will be one club, I will go 13 choose 1, and then from the other 39 cards, choose 4 more. Case 2, getting 2 clubs, that would be 13 choose 2, and from the other 39 cards, I'd have to choose 3 more. Case 3, 3 clubs. This is sort of a long-winded explanation, but it works, so that's why it's good. 39 choose 2. Case 4 would be 4 clubs. 13 choose 4, and then of the other 39 cards, choose 1. And case 5, all 5 clubs. So you just have to choose 5 from 13. Since it's a cases question, once I calculate each of those separately, all I need to do is add up my cases. And that will give me the right answer. So now you have 3 methods that work. Choose 1 club, mix them back in, choose 4 more. Use the not strategy, take all of them, subtract the bad ones. Or use cases, count them all separately, 1 club, 2 club, 3 club, 4 club, 5 club, add them up. They all work. Or do they? Or are none of them right? Have I just been lying to you this whole unit? There's no such thing as permutations and combinations. We now have our numbers, and now we have to, at least one of these is wrong, because they can't all be right. So the next thing we have to do is we have to come up with why. Why is one of these wrong? So the total possible poker hands possible that we figured out earlier was just about 2.6 million. And method 1 says of those 2.6 million, 3 million, 3.2 million have at least one club. Can you see the logic problem we have here? There are more poker hands with one club than total poker hands in total. And that doesn't even include some poker hands that we haven't counted. What? That doesn't make sense. So that is the reason why method 1 can't be right. Now the next thing that we have to look at with method 1, and I guess I'll tell you now, method 2 and method 3 are both right. What happened in method 1 that we got such a big number? Well, when you get a number that's bigger than you should have, sometimes that means you've counted things too many times, or you've overcounted, or counted the same thing more than once. And sometimes the best way to find out where I went wrong is to go through a couple of examples of what you could have picked in here. So in 13 choose one, that means I took my 13 clubs and I chose one of them. Which one would you like to pick? Doesn't matter. Just give me an example. 6 of clubs? Ace of clubs. Okay. So we start by choosing the ace of clubs. Then I put the other cards back in the deck, I shuffled them up, and I started pulling out other cards. I happened to get maybe the 5 of hearts, the 7 of diamonds, the king of hearts, and the 2 of, that's a heart. That does not look like a heart. I'll work on that. There we go. King of hearts and the 2 of clubs. Can you see that that would be one possibility in this situation? I'm not going to list all 3.2 million. Don't worry. Okay. But another possibility is when I chose the 13 choose one, I could have chosen the 2 of clubs first, right? And then I mixed the other cards in, and I happened to pull out the 5 of hearts, the 7 of diamonds, the king of hearts, and what do I choose here? That's a problem. The ace of clubs. Now, according to what I've written in method 1 would have counted these 2 hands as different. Why are they different? Because I chose a different thing to begin with, and then I chose 4 more cards. But the order doesn't matter in the end, and those 2 hands are the same. So if we are going to summarize what went wrong in method 1, is that if I look at my 2 decisions, I have overlap there. I could choose the same card in decision 1 that I could choose in decision 2. I could choose the ace of clubs in the 13 choose one. But if I didn't, I could choose the ace of clubs later in the 51 choose 4. And if you have that overlap, you create order. And that causes a problem. In fact, it just made us overcount by about 1.2 million. Just a small error, same kind of like change error you get at the grocery store. You buy some groceries and they're like, oh, I accidentally gave you $1.2 million extra in change. Happens all the time. It ends up being a huge mistake because we're off by so much. If you look at the cases, notice in the cases, we always do 2 decisions. But in the cases, well, not the last one, I guess. But in the cases, can you see that those 2 decisions don't overlap? We choose clubs and not clubs, clubs and not clubs, clubs and not clubs. And because they don't overlap, that allowed that to count that properly. But it's a hard thing to see the logic of why method 1 went wrong. Of all the methods, method 2 is probably the simplest. It's a great example of where the not strategy can be used because it's really easy to count all of them. It's really easy to count the bad ones. And all subtract the bad leaves us with at least 1 club. It's the same idea as the cases counting it directly, but it is much quicker.